Okay. All right. Let me move this guy. Okay. Okay. So oh, wait a minute. Do you see my screen?
Yeah, I see it. Hmm.
Okay. All right. So your model. Let's go check at the bottom base. So I want to make sure where you are. Okay. Seems like you drew the map.
Yeah, I drew it, but when I go to the
Hmm. Good.
to look at the parameters, it
Hmm.
doesn't. It's all just purple.
Yeah. Okay. So those are column. Okay. We see this. All right. I'm just look down and see. So where you are. So first of all, clicked and checked the, okay, material properties, section properties, 9 feet mat C6. So go to define. I'm checking slab mat properties. Okay, 96 is using 6,000 feet. All right. So material, usually because if you just started new new project, good to
Hmm.
set all the material property, especially concrete, we don't have a data bank. So
Yeah, no. Hmm.
steel, we can use the AISC section properties, but the concrete, we don't have it. So let's say if you continue, you're the structural engineer, you keep using that ETABS file, good to have a one template and keep using it. Otherwise, you may have to redefine the section property and material properties every time.
Yeah.
Right, but I think it's 6,000 for concrete. I think what you need to double check is Young modulus. Typically, normal weight concrete 150 P pound per cubic foot, and Young modulus is always the one we have to be careful. Always double check. And the unit should be correct. So, okay, I think you already defined the thickness of the mat,
Yeah,
and
I even tried with
yeah,
different thickness of maybe 7
yeah, I
because
think
I thought maybe it was too strong.
yeah.
But it stayed the same. It didn't show any difference.
Yeah, I think eventually we need to optimize. So the beginning, it's just 9 feet is just one, just a rough
A
number.
general, yeah.
So we need to do kind of iterations. So let's say first of a structure. Let me just check your model where you are. Just checking the moment release. So this graphic mode standard. Okay. So you have all simply support beam. This one
Should I just make it one entire slab?
or entire or assume it's dummy because we're not designing it. We are focusing on the composite slab outside.
Got it.
Actually, this in realities we're not using the that fully.
Hello?
Okay. We're gonna use a one-way slab like this, and this one's not gonna be the metal deck slab. This is concrete slab. So, but you're not focusing on this. Let's say slab. So I'm gonna assume 6 inch slab is typical. So 6 inches. We can use a membrane. So no contribution. Use a special 1A load distribution. Okay, so I'm gonna assign the shell slab 6 inches slab. So this is 6 inches slab. I think it's a
Hmm.
concrete slab, right?
Yeah,
So
yeah,
I think at this point, you don't worry about this. I think let's focus on the slab and composite beam design outside. But typically, since this is a concrete construction, we're gonna use concrete beam and concrete the slab.
yeah.
Actually, we needed some bunch of the opening for elevator bank and stair opening. But all right, so seems to me okay. Looks What size you have it?
The what?
The
The
beam,
walls?
the beam design.
Oh,
Okay, I'm looking at the 16, 21, 21, 16, 21, 18. All right. So you have a various sizes because of a span is different, right?
yeah,
So
40 and
40
30.
feet, so 21 by 55. Okay. I'll say that makes sense. Typically, you can start with roughly the length divided by 20. So if this is a composite beam, maybe the maximum size, I will just try 40 times 12 divided by 20. No, 20 W24. But since we are using composite actions, I think
Hmm.
W21 seems okay. Right. So somehow you need to start with or spot check the beam size you're getting is reasonable or not. I will just usually use L over 20. So length divided by 20 is something the maximum beam size if this is normal condition. So okay, so you have okay, looks reasonable size for now, right? So every size is the same. You copy it, and then so I assume every floor is you copy it, right?
Yeah, yeah.
Okay, okay. So let me turn off this. So now I'm gonna check just load patterns. You have a Delo self-aid included, live load, SDL, this is construction live load for composite beam. Okay, wind. This is ultimate wind load.
No, that's
Yeah,
just, yeah,
power
ultimate. No, no, service wind load with the factor of point.
Yeah. So this is all 12 cases we are considering it. So this is ultimate wind load. And this is a service wind load, 98.
Yeah.
This case one means this is only one case. So that this is the wind in X direction. So
Wouldn't the wind be the same in the X and a Y just because it's symmetrical?
Uh, no, yeah, it's almost symmetrical, but ETAPs, we need to guide them clearly, right? So the wind load case is only load one case, wind is blowing X direction. So I would say this is wind X, service wind. I'm gonna copy Y again, right? So I'm gonna create another win service and win Y, but here I need to change to load case one, but I need to tell the orientation. So this is wind blowing in Y direction,
Yeah.
right? So because this case one, this is types thing. So this is when you say one, it's only one load case, but you have to define the direction, which
Mm,
direction, right? So this X and Y, each individual just wind load based upon basic of 98 mile per hour. So this is service wind load. Okay. So, okay, let me just now turn on the diaphragm extend. So, okay, you assign all diaphragm every floor, right? If you rotate it, you have all the diaphragm at each
mm.
floor. One thing that you make sure, okay, this is basement. So we don't need the
A
diaphragm
diaphragm.
here
Yeah.
because we have a boundary condition here. So I'll go discontinue this floor, but the the floor above is we're gonna have a diaphragm.
Hmm.
All right, so let me just save it. Now, since everything is set, now we're gonna check the boundary condition for mat. So you assign this area spring separate modulus, which is spring property, area spring. So this is what we discussed. Maybe this is for now, we may have to run a few rounds, but I'll just kind of keep it as it is. So this is a 480. So this is only spring work and constraint in vertical direction.
Yeah.
because if we don't have an XY constraint, this building is going to move horizontally, right? So, okay, hold on. So I'm going to just click this node. Did you assign the boundary condition?
Well, yeah, in the X and Y direction.
Oh, you already did. Okay, good.
Yeah, yeah.
Okay, so that then is ready to, yeah, run. So I'm gonna run the model. Let's see. Okay, let's see. Okay. So default dialog displacement is exaggerate, so don't worry about it. Okay,
Yeah.
so first thing, always your model validation check. So I'm gonna just put the deform shape when, oh, okay, this is, we didn't change the name, the load case. So this must
Oh,
be
okay.
WinX.
I'll change
Service
it.
win. Yeah, this is service one. So let's check the win extraction. So extraction, WinX. Okay. So okay. Oh, this too slow. So okay, we are checking that your win loading is makes sense or not. Oh, turn off this. So actually the plan view show much faster, right?
Hmm.
So wind blow in X direction, push the building in X direction. Now Y direction here, I think you can click this
Okay.
direction and animate. Obviously, see that?
Yeah.
So this is a wind Y. So now what you can guess here, here's a win. This is total 12 cases, right? Here is, so you said there is some number. So we have a total of 12 cases. So obviously number one, you can guess it, win X direction, right?
Yeah.
This is ultimate win load. Now, second is in win ultimate win load in Y direction, right? And then third is I think X direction with eccentricity. So let's see. We have some torsional. What? Wait a minute. Oh, no. Okay, this is three here. So,
Oh, I see. Yeah.
right? So this is actually the win X, but with some eccentricity, 15%
Yeah.
eccentricity. This is all the code requirement. I will show you maybe tomorrow. So there is a, you know what? Let me show you. No, actually, yes, here. Uh, Canvas. 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 So you have to get used to the ASC7 for wind load. Because I think because the code keep evolving every 4 years, you need to
Stay up to
understand
date.
the background, because you cannot just interpret the code without knowing the history. Is really
Hmm.
sometimes is challenging. It's hard to understand. So the AC7. Okay, here. What is dead load and live load? Did I include? Okay, okay, here. So this is 7 to ASA 7-10. 16 is pretty much similar. So the diagram, basically all directionality here. So no, this is a Gable loop. Okay. Oh. This is a roof. Where's the wall? Oh. Uh, this is gable roof. Stop. Should be somewhere here. Oh, here. Okay. Yeah, find it. So we have a total case 4.
Hmm.
Case 1 is our 1, wind blowing X direction, but wind can blow minus X too, right?
Yeah.
Right, wind X and Y. So it's a positive and negative in X direction. The Y also have a positive and negative. Totally just X direction and Y direction without any torsion. But case 2, see that X direction, but we need some consider this accidental torsion effect. So this is a code requirement, 15% torsion. So we have X direction with eccentricity, positive eccentricity, negative eccentricity, right? Y
Hmm.
direction too, because the building may be that doesn't have to be symmetric or doesn't have to be square. So we have to consider all this type of effect. Now, case 3 is most likely diagonal wind direction. So square root f prime c, square root f square, x square, y square effect. So diagonal wind direction, but it can come from all 4 directions. So this is K3 can explain that the diagonal the wind effect. Case 4, you see also diagonal plus eccentricity. So this is all eventually total 12 cases that we need to consider, but also plus and minus. So I think ETAPS, these 12 cases, I think apply, especially number 3 is when X with the eccentric, positive eccentricity effect. 4 might be negative. I think, yeah,
Yeah.
another direction eccentricity, right? So,
Hmm.
okay. So looks like the building model looks okay. Let's say, so what you need to do is based upon current wall thickness. I think it seems like you have a huge, huge,
Huge wall.
the core
Oh.
dimension. Is it 80 feet by 80 feet? Oh my gosh. Your building, this core can support more than 100-story building.
It can't.
Yeah, you can. You can.
Oh, okay.
Um, Maybe I'll show you later some other project, Ping An Tower, Shanghai Tower. Oh, let's do this. So,
Do you think that's why I'm having trouble with the
huh?
foundation?
No. I think that doesn't. So, maybe it doesn't show the dimension, but I'll show you. Okay. This is 100-story building, 600 meter, so 2000 feet.
Yeah.
The core wall, if I remember correctly, it's about 60 feet by 60 feet, something like that. But
Oh,
yours is
wow.
88. But anyway, uh, so the wall thickness, I think you currently have only one wall.
No, I have two.
Or you're using different.
Yeah.
Okay.
I'm currently using the I forgot. It's there though.
Okay, let's see. Let's see. Wall. Okay, good. Do you have a beam?
Yeah, I do. But
Okay.
it's integrated with the other beam.
Oh yeah. Okay,
I
so
I
what
have
am
a
I doing
core. I
here?
made the core subgroup if you
Yeah.
wanted.
Oh, okay. I'll just do X, Y. I'm gonna select all these 3D members, show only members, and so Control D.
Okay, wow.
So yeah, so I only select all the wall and beam. So now you said you assign two different sides. Okay, good. So you have
Half basically cut in half.
18, C7, 16, and 6. Okay, good. And link beam here, so you matching the thickness?
Yes,
18 by 30?
18 and
Good.
16.
Okay, 16. Okay, things for now looks good.
On the graphs, I showed
Mhm.
C9 and C8 and C8 and C7 too, just for
Mhm.
comparison.
Oh, okay. Or try all 12 inches because your core wall is huge. So let's check here. Deflection. Probably
So it's well before it's probably 9.5. Yeah,
story,
the
story
service.
displacement. 10, 10 inches. Service win X. 10 inches, right?
Yeah,
And then Y, yeah, obviously symmetric. So 7.9. Oh, slightly different. Hold on. So 7 inches here. Extraction. 10 inches here. Why?
yeah. Why is it different?
Wait a minute. Something different? Mm,
No,
is that symmetric? This code?
it should be
Oh,
because
yeah. Okay, different. Yeah.
yeah.
See that?
Oh,
Structure,
yes,
because
it's
this one doesn't
braced.
have opening, right?
It's
So
braced.
distraction, but we have this opening here, right?
Yes, I see.
So if this is symmetric, I think Y direction it should be stiffer.
Yeah. That's why
So extraction, we have what?
extraction
Extraction,
is the 7. No,
extractions,
no, that's the stronger one.
10 inches, but the Y direction is deflection is lower, 7.
Oh, okay. Yeah, makes sense.
Right, makes sense because stiffness, entire core, I think this direction is much stiffer because this entire wall. But
Oh, okay.
next direction, you have this guy. Okay.
Mm.
So, yes, so you can summarize this, maybe two run, right? Various,
Yeah.
I think that's a pretty good, you need to know how to use Excel. I
No,
show
I already
you.
did that,
Yeah.
but I'll have to. Since I thought it was symmetrical, I only did it for
Yeah.
one. But I'll add the
Yeah.
other
I think
direction.
that's cool. You could explain this. Your building looks symmetric, but core is not symmetric because of this. So
Okay.
base one is symmetric, but the core wall or overall core system is symmetric. You could mention it Y direction because this is solid wall, so has a more stiffness. So you end up with 7 inches versus 10 inches in extraction, right? So this is
Yeah.
okay. Okay, so move on. Maybe you already know you can kind of pull out all the summary, material summary, right?
Mm-hmm.
This is something I show you. So you can summarize it tons for steel, volume for concrete.
The material takeoff.
Oh, this is only selection. Yeah. So hold on. So I need to turn on, stop. Okay. So show selection only member.
I think maybe we have to highlight all of them.
Yeah, typically. Okay. Okay, yeah. Yep. We have to
Okay.
highlight all. You can summarize it. Okay, good. So that is good. Now let's check the match. So I'm gonna move down to base. But before you do that,
Mhm.
you always should be interested. Let me turn up the beam raise slab. So let's see
The axial force.
column. Your column design is done. Okay, seems okay. You seems like you run it, so you got different sizes. So basically, you could check. Yeah, 1.2 that 1.6 live road actual force diagram. So this is gonna make sense, gradual increase, right?
Yeah.
Okay, good. So obviously you see how many loop combination here. 1 to 14, 2, you can see the 1.2, 1.6 live road. Good. So just in case a live road, you can use the live road reductions. You typically, I I apply the reduction factor right here. Oh, we already applied 0.5.
Yeah.
Okay, good. So I think this plus minus okay, but we can use up to 0.4. But since some upper column, I think cannot be 0.4. It's totally based upon cumulative gravity area. So most likely at the all the way down, maybe five floor down is we can use 0.4, but upper floor, fifth floor, likely it varies. So I think 0.5, I assume it's gonna be covered mostly reasonably. Okay, so your model seems okay. So I'm gonna move back to base. I'm gonna turn on the slab floor. Okay. Did you draw the design strip or not yet?
No, I haven't gotten past this point.
Okay. So now I think, oh, why not? So I'm gonna turn off this. So design strip is Control D. Okay. So you can draw X direction and Y direction. So I think design strip here. I know there is no absolute. They absolute the number, but just for simplicity, I'll use 10 feet. So 10 feet is 5. So 66 by 60, right? So 60 inches left and right. X in the strip lay X. So first, oh, okay. I need to draw from, right here. Maybe I can draw from here to here. So I'm gonna start from here. If you,
I thought this was done in a later step.
no, I think so we can do that now. I think the first one is a finite element method. I will show you both.
Okay.
Yeah, because I'm gonna draw. Okay. Okay, so I need okay, good. So where is this? Okay. So design strip. Okay. 1, 2, 3, 4, 60, 140, 200. So I need to copy linear Y direction, 10 feet, right? but I need 20 of them. One more. So what? Oh, no. Yeah, this one. Okay, so my design strip cover entire my mats in X direction, right? So
Yeah.
design strip is 10 feet wide. So we're collecting the forces, member forces, shear and moment based upon this design strip. So now second one, maybe a ton of this. Hold on. Okay. Okay, right there. Now strip layer to B. So now Y direction, click it, replicate, 10 feet and X direction. So if this is same symmetric, 21.
Yeah, it's 20. Yeah.
Oh, hold on. I click the wrong one. Okay. Oh, I click the beam. Okay, now I click the strip. Okay, so I cover. All right, so I draw the design strip. Now X and Y. So it's okay. Okay, let's change to building view down to maybe base. So we'll see. Okay, I'm gonna turn off this. Okay, now let's run this model again. Oh, hold on a second. Oh, no. This accidentally apply.
Oh, yeah.
Okay, hold. Hold on. Maybe I have extra. Okay, but this one I deleted. Okay, so I'm gonna run it.
What were the strips for again?
Hmm?
What were
Strip.
the, yeah.
This is basically the kind of design purpose. I think design strip came from flat slab design. Somehow we, as an engineer, we more kind of prepare to play with the member forces, right? Shear or moment. So because it is a finite element software, I'll show you here, right? So what you're gonna get first, let's say, I think first option, this one give us the let's check how we explained it. So after this model is ran, what you need to check is soil bearing, right?
Yeah.
So total dead load, SDL, and live load. So this is one example, that plus live SDL and total gravity load, right? And
Hmm.
then I think you can just open your the foundation design foundation book spread frame. You check the soil bearing based upon the total design that the gravity load and see what is your soil. So let's check the soil bearing stress based upon your building, right?
Hmm.
So here we have a 710 PS KSF, who goes down, getting smaller, right?
Yeah.
It's all negative, it's all compression, right? Since we have a core and also floor, so core is usually taking most of gravity load because the
Hmm.
side and all the loading is concentrated. So you see the maximum occur at the center and gradually reduce, which makes sense. So this is so stress. Okay. Maybe put in 3D might be better. Okay. Okay, this is my foundation. If you want to see the deflection, not the direction, then you see this is dish effect. No direction, deformation. The plus STL and arrive road. Contour vertical directions. Vertical direction. Okay. Oh, because of this unit, I'm going to change to inches. So let's say value -1, -0.5. Let's see what, 0.39. Okay. -0.359 minus, let's see, sure. Okay, you see it? Maybe I'll exaggerate. So graphically, okay. Yeah, this is matrix because more loading is coming from center, from the core. Deflection diagram show, because the soil pressure diagram you already saw it, right?
Yeah.
Maximum occur at the middle. So this is actually too much. So 500. This is exaggeration, but we are talking about less than half inches. Look at this, right? 0.42 inches. Yeah, something like that slab and beam, it deflect vertically, even though we have a spring, constant spring. So mat will deform, but magnitude is very small. Let's see that 0.4
Yeah,
inches.
0.415.
So, okay, seems reasonable. We don't want this deflection is too significant. If this deflection is very significant, that means your soil relatively weak, right? The geotech engineer, we assume that our spring constant 480, that is based upon 20 tons. Is it 20 ton? No, 20. Yeah, no. Yeah, 10 ton. Yeah, so 20 KSF, our soil bearing capacity. So this is something associate spring constant. We currently use it. But if this number is much kind of double or triple, then obviously that means our soil is relatively weak, soft, right? It kind of causing this kind of mat deflection. Then geotech engineers likely they'll recommend that using deep foundation, not mat foundation, because the soil is relatively weak. So this is a 480 seems is equivalent to rock, weather rock. So I think at this point, this is reasonable. What you need to now check is this is the mat
Stress,
thickness,
yeah.
by the shear. So we usually check every load combination, but we're gonna check the for example, 1.2 dead, 1.6 live load, and here shear stress. That
The
vertical
S13
shear
and
stress.
S23.
Yeah, S13, S23. This is something you need to get used to the sign convention here, local axis. When you see this, red is local number 1. This is orientation, local axis 1, green is 2, outer plane is 3. So when you look at 1, 3 is the stress on this plane. When you cut this section, 1, 3, right here. So that is the stress as 1, 3 is going to show the shear stress on cross section on 1, 3. And as 2, 3 is the shear stress on cross section as 2, 3 plane, right? So I think this is kind of similar to your slab, the beam design, but you may get confused because we are talking about two-way direction. So this is something more finite element software. Let's turn on this. So let's set it up to 222 something, because our 6,000 psi, 6,000 psi concrete. Sure, two-way punching shear, two-way shear capacity is 0.75 times 4 times square root f prime c, 6,000. So this is our shear capacity, concrete shear capacity, PSI, 232 PSI. So let's say 232, 232. Okay, in generally, yeah, the shear stress is low, except, yeah, they're close. It's not that much here. Yeah, local, but here much smaller, right? Number. So I think we can maybe average it somehow, roughly average it, so weight it. Otherwise, if you're using this shear stress, this is more concentration, shear stress concentration, you end up maybe increase the mat thickness, but this is, I think, is the localized shear stress. So I think your 9 feet is way enough. So 2, 3.
So I would have to use a smaller thickness.
No. If you reduce the thickness, I think you're gonna see the more.
Oh, okay.
Yeah, the higher shear stress. I think so far you could just show this, right? One example, 1.2 that 1.6 live road, shear stress 1, 2, 3, S2, 3, and this is your concrete shear
capacity.
Capacity, and then you can mention it. This is a shear stress. It's a localized shear stress, right? As needed, you maybe end up to increase the maybe I can add a shear reinforcement as needed, but I think you can just conclude as this is the shear capacity check.
Got it.
Okay. So now we did a soil bearing stress check here, right? And then basically this is only that plus live road, but you typically, if you're interested, you could do that combination of wind,
yeah,
this extraction, so 0.75
and 0.75.
right? So service WinX. That means you probably no, let's do the Y too. This is Y direction. So what you could guess, you turn on this, you have a gravity effect and you have also lateral effect, right? So this is the high stress is shifting to the right because the wind is blowing this direction, right? So this is something cool. Just okay. Now let's move to the mat design. So I think since everything is set, we'll go to design and concrete slab design. But one thing I probably add here, here minimum cover for slab. So this is default for just typical slab design. So since we're using mat, this clear cover is much bigger. So to prepare the bar, we're gonna use number 11, right? So
it's like 1 inch.
Yeah. And this is we need minimum 3-inch cover, 1.5. But since we have a multiple layer of the bar, I think eventually maybe 3-inch clear plus another 1.5 or 2 inches. So for now, I'll just assume 5 and 3. This is something we need to adjust it based upon total number of layer of bar.
Okay.
It's based upon most bottom face of the concrete to centroid of the rebar. Centroid of the rebar. So that means you may have to kind of finalize it based upon your final decision,
Design.
right? So now which rebar you want to put in next, inner versus layer? Doesn't yours is symmetric, most likely symmetric, doesn't matter. But usually I put the inner layer to the wicket minor direction.
Mm,
Our case is if we don't have much because they are almost symmetric, right? So,
yeah.
but usually that means the major direction causing more bending moment. So you want to put the rebar to outer layer in order to gain the effective length, right? Effective length.
Hmm.
So that is our slab and beam design method. So here, I'll just slip it in a layer in the B direction. We draw the design strip in B in this direction, Y direction, which is here. Y direction is this. Oh, okay. Okay. Hmm. Okay. Well, sometimes myself.
Oh, I think you have to show all objects now.
No, this one really. Oh, oh yeah. Okay. Oh, here is design strip zone. Okay. All right. So at the base, okay. Now, what I think you could just play around the strip force and see the 1.2D, 1.6 live road bending moment diagram. You see like that,
Yeah.
right? And Y direction, you could show like this. Okay, makes sense. The positive and negative because this is continuous spring. The med is
Yeah.
the continuous spring, so you're gonna have a positive and negative like this. So okay, so I think you could show this, and what we're gonna do, go to slab, concrete slab design. Did I select the mats? Okay, I have to select the mat, otherwise you're running entire floor. Go to design. Now we're gonna check design combination. It's S1 series, right?
Yeah.
Well, this is all the low combination I'm gonna use for strengths design. So now ready to design. Okay. Okay, so now it show all the rebar area, required rebar area. So you can just play around, but I think most here, interesting stuff is here. We're gonna use a minimum reinforcement. There is a 2 meter finite element there, right? But usually finite element method is showing some intensity of required reinforcement, which somehow is not really intuitive, right? But give us
Yeah.
in general ranges intensity required steel intensity where need more than right less others. So this is kind of give us the overall just contour, but it's not very intuitively. So I will just use a strip method, right? And I'm gonna show the bottom bar first in X direction first. I'm gonna use the rebar. So I'm gonna use number 11 bar. But I'm gonna also additional bar. I'm gonna use number 11 additional bar. So this is the kind of setting I'm gonna turn on. So then this means if I provide number 11 and 12-inch on center bottom bar in this direction, you need additional bar this much. So, okay, maybe what about 6 inches? Okay, 6 inches most likely cover major area, but you still need additional bar under the core wall, right?
Yeah.
And some locally more. What about 3? Okay, 3 is most likely cover entire mat. You still have some local additional reinforcement needed here. So I think explain that number 11 is 3 inches is not practical. Number 11 at 3 inches spacing is not practical. So I'm gonna bundle it if I decide to provide this. Bundle 3 bar number 11 together, right? And I'm gonna put in 9-inch on center, right? But typically I usually bundle two. So maybe, yeah, number 11, 6 is still quite dense. I'll consider multiple layer. So if this is the case, I maybe put the 2 bundle at the bottom layer and another number 11 I'm gonna put on the second layer, right? So it's multiple layer I'm gonna consider it,
Yeah.
right? So Y direction probably similar, yeah, because you have a symmetric. So what you can do, you could just for now play around this, okay? Show bottom bar, XY direction, right? So what you can describe that, okay? You're the engineer, you're the designer, you're gonna provide number 11, 3 inches on center, which is equivalent to 2, number 11, 6 inch on center, or 2 number 11 at 12 inch on center is your typical bottom bar, XY direction, and then additional bar on screen will be provided. That is your answer, right?
Yeah.
Yes. So it's up to you. Maybe you end up with 4 inches, then okay. Most likely number 11, 2 number 11, 8 inch on center, and whatever this additional rebar we're gonna provide locally.
So I'm only worried about the bottom rebar, not the top.
No, you're gonna do it the top bar as well.
Oh, okay.
Yeah, same thing. So top bar is usually a little bit less. So let's say, oh, it's all gone. 10 inches. Okay, so seems like 9, 8. Wow.
That's
So
weird.
wow, so gone. So this is quite, yeah, something you could say you based upon this, yeah, okay. Maybe you could use number 11, 8-inch on center. Oh, right? That's will most likely cover, right? So if you're using 9-inch spacing, you still have to add this much of rebar, but 8-inch spacing will gone, right? So I think that you might be decide number 11, 8-inch on center for the top bar. But bottom bar is you need more. So you could just kind of I have 0. So you could use this bottom bar here. Okay. All right. So this is kind of tool you just use it to scare away because ETABS already calculate the required rebar areas. So now it's engineer judgment that which bar you're gonna use it. You're gonna bundle it. You're gonna use some closer space, wider space, but bottom bar, top bar, something you can turn on and off and kind of summarize it so that you propose what number of bar you're gonna use it for bottom bar and top bar.
Yeah.
Okay, I think that's it. I think this model seems okay. So I think for deflection, you can show few run with the various wall thickness and show the summaries. I think that will be good. And your and then later on, and then since building is too bulky, so if you want to do this, maybe why don't you, I don't know, somehow drop this
Oh, okay. I see.
a little bit, some kind of dynamic looking,
Yeah.
right? You could just delete something and make something set back a little bit. It's up to you. And later on, you could extrude and export to the XF file. So like eventually we're gonna create the nice rendering.
So how do I go about printing the model? Do I have to make an appointment with Makerspace?
No, I think you I think tomorrow it will be open, tomorrow and Wednesday. So anytime. But since you're a student, you could use it. But have you used it before?
No, I've never used it.
Okay, then maybe I'll send, I don't know, but you need to make some CAD file, right? What to, so why don't you kind of
Because I can't just make it into an STL file.
STL?
Yeah, because but
STL?
that would be a 3D printed
Uh,
thing.
no, I don't. ETABS STL, I'm not sure. You may have to, I don't know. I'm not good at the ETABS STL, but if you know it, how to do so. But doesn't have to be a huge model. But if you wanna using laser cutter, yeah, laser cutter is sometimes simple. Um, and yeah, it's all up to you. It's uh, let's see.
So this file, do I have to send it to somebody at Makerspace before going?
No, no, no. But you, yeah, I'm not sure this ETABS you can just print right away. You may have to clean up. And basically, you need to know how to use a 3D printer or laser cutter. So, the the model you created, somehow we need to think about how to create it using Makerspace, laser cutter or 3D printing, or somehow current model you may have to simplify because current model is relatively huge. So let's see. So maybe I'll email everyone if you're interested. So either we can meet at the Makerspace either tomorrow afternoon before the class or maybe Wednesday so we can clean up and print.
Yeah, because tomorrow I can tomorrow before the class, but I have to leave because I have to work
Yeah.
at night.
You're working. Okay. Oh, so tomorrow you cannot make the class? Oh, you're okay.
No, I can't make the class,
Right,
but
right.
I can be there
Yeah,
before if
yeah,
the group goes to
yeah.
Makerspace.
So what, because the building is, we need to simplify. So one thing is maybe the core, probably, where is that tips? So maybe with this, we can, wait a minute, elevation, elevation. Yeah, something like, but still a lot. So we can clean, but we need to, because the laser cutter is just a line work, so we need to draw the line. Maybe
Hmm.
we can simplify. Let's think about it, what to clean up. Maybe we can cut this only face by face. Okay, let's think about it. So You don't have to cut this tall. There's too many cut.
Because
So
what
this
if
is
we
it.
cut it floor by floor and then I just individually glue all the columns and
No,
stack
no,
it
no,
up?
no. That's a lot. So I mean, something. Where did I? Okay, Rhino. So something like that. So something like that. This is the one example, the brace frame, right? I draw this way and cut it. So we'll see. I think if it maybe tomorrow, what time is it? Okay, yeah. Uh, Tomorrow anyway. I'll be there maybe 4:30, something like that. So maybe
Yeah, I can be there at 4:30.
yeah, I'll be there. So if you guys actually bring laptop or some of them, we need to simplify your elevation like this. We can cut it face by face. We can glue together.
You got it.
But obviously we need to simplify because that just yeah scale is different.
Has
So
anybody else printed it yet? Or
not sure. I don't know yet. So yeah, this is really big. So we can just simplify this and make a small model. Just to show something profile like this. And then we can cut side by side. And yeah, let's cut side each face and then glue together. I think that may be enough. Or we can cut just representing just each setback level plate. So we can cut it. We can print this, glue together.
floor by floor?
Not every floor, just some few floor.
Okay, yeah.
Yeah. Okay, but I think we need to just draw the line works. Otherwise, yeah, this will take a while. So maybe let me kind of think about it. I will just do something one example for tomorrow. If you can come, maybe anyone is showing up, I think we'll kind of clean up. We'll
At
cut it
4:30?
together. Yep.
Okay, yeah, I'll be there at 4:30.
Okay. Okay, sounds good. I think your model seems good, So, let me just email you back.
Yeah, I'll play around with the rebar tomorrow.
Okay, I will send two model and take a look at it. And
Okay.
maybe see you tomorrow for around 4 o'clock. I need to figure I will kind of draw simple model. So your model is relatively huge. So because I would also have to scale down to the building side, building the plate, the
Yeah.
door side, yeah. So let me think about
Okay.
how to do this. Yep. Okay. Sounds
Thank you,
good.
Professor.
All
Have a
right.
good night.
You too. Bye.